All right, hi everybody, my name is Matti Thurston. Today I'm going to be presenting a thin film approach to a superconductor with the highest transition temperature at atmospheric pressure. I'm with the Schlom group, so located out in the Paradigm Lab in Duffield, and today we're going to start off by talking about superconductors. What are they? So as a brief definition, a superconductor is a material that exhibits zero resistance and ejection of magnetic flux at a specific temperature. These materials are characterized by the temperature, purity, and everything that they operate at, and they're evaluated at a transition temperature. So the transition temperature is a temperature at which, if you continue to drop the material, when you hit the transition temperature, resistivity will go from some decreasing value all of a sudden down to zero. So if you look at this plot over here of a normal metal versus a superconductor, you can see a normal metal, as you drop temperature, it's going to just slowly level off. Whereas a superconductor, you're going to hit a point, this TC value, the critical temperature or transition temperature, and that's when it's going to drop to zero resistivity. At the moment, current applications for materials that are superconducting include medical operations, such as MRI and NMR machines, and then scientific applications, such as the magnetic lines in the Large Hadron Collider, CERN. So, the golden question right now with respect to superconductors is, can a higher temperature superconductor be created? The current best superconductor, or what is described as the best, was discovered just a couple of years ago. It's the H3S structure, which you can see over here. And it's identified by this plot of the year versus transition temperature. And so the best performer is right here with a 203 Kelvin performance temperature. But the issue is that that requires 90 gigapascals of pressure to make it work. So imagine that you're trying to make a smart grid, or an electrical power transmission line, or a maglev train, spintronic devices, quantum computing. Do you think you can put 90 gigapascals of pressure in there? Not really. So we have to then look at what is the best performer at 1 atmosphere of pressure. And the current best is this mercury-based cuprate structure, which I know it's a little bit hard to see, but it's in this area right here. If you were to draw the line down, you can see that it was identified in 1992, 26 years ago. That was when the last achieved advance in an atmospheric pressure superconductor was made, 26 years ago. So, these structures, all of the ones that perform at 1 atmosphere of pressure, they're generally derived of a cuprate structure. Cuprates are incredibly well researched. In fact, since 1970, when some of the first ones were coming out, there have been nearly 17,000 published papers. And the Nobel Prize in Physics in 1987 was actually given to the discovery of a lanthanum-based cuprate structure. The general structure required for these cuprates, and I'll walk you through the structure in a second. Basically, you need copper oxides in singular sheet planes that are within 180 degrees of one another, so you can imagine square sheets of copper and oxygen. And the copper in those sheets are in +3 to +2 oxidation states. And then you have a superlattice of spacer layers, so basically perovskites, dopant layers. This allows you to have just the general structure around the cuprate layers. So this structure right here is BSCCO. This is the structure that's used in the Large Hadron Collider lines at the moment. And what you can sort of see are some cuprate planes right here, so they're perfect flat planes right here, cuprate plane right here, and then these are all just stabilization layers on the outside that have different characteristics. Each of those stabilization layers have different impacts on the performance of the cuprate. But, as mentioned, 26 years ago was when the last achieved atmospheric pressure cuprate, or better cuprate, was discovered, and so very little has happened since then. In 2008 though, E.V. Antipov and A.M. Abakumov in Moscow, they published an empirical set of rules that describe basically how you can design these cuprate structures based on every single top performer thus far. Antipov, in fact, if you go back to that plot I showed you of year versus transition temperature, he discovered the second best performer. It's a thallium-based superconductor, and so he's spent 35 plus years working on these different structures. And so these empirical rules allow us to have a way of considering what a cuprate structure needs to be superconducting. And so the critical rules can be summarized into 6 critical rules. Rule number 1, the copper-oxygen planes, if you imagine those sheets sort of like up here, these planes right here, they need to have a bond angle of about 180 degrees plus or minus 4 degrees. Not much room for error. The second rule, you have to have a specific formula with highest transition temperatures appearing when you have about 3 cuprate planes per unit cell. The third rule is that you have to have cations of a single type around each side of those cuprate layers. Rule 4, in-plane lattice parameter of A less than 3.85 angstroms, so that's just been observed in every single cuprate performer. Fifth rule is that you need to maximize apical oxygen distance. So imagine that you have these oxygens right in here, which are in-plane oxygens. You can imagine though that there's also oxygens above the copper and below the copper. That's the apical oxygen, and that's going to become a little bit more important in a second. And then the sixth rule is that you must hold dope all of these materials so that you get a formal oxidation of about 2.1 to 2.2, 2.2 to 2.3. So in that range roughly is okay. Now I'm going to highlight 3 rules in particular, Rule 1, Rule 4, and Rule 5. These will become important in a couple of seconds when I get to a little bit about our structures. Something that's interesting in this published paper by Antipov, 2 conclusions were had by Antipov. The first rule, or first conclusion was, if you could make a thin film that has all these characteristics, you might see superconducting behavior. But at the time, that was not possible. His second conclusion was that he could do nothing else in this field because solid-state chemists had run out of ideas, and so he left the field after 40 years, which shows just how crazy of an idea this sort of became. Nobody wanted to touch it. He's now working on, I think it's thermoelectrics. So, what are our research goals, given that we now have these list of empirical rules? Well, our first goal was to use first principle analyses to identify cuprate heterostructures that better satisfy Antipov's rules than anything before. This particular formula unit, lead, titanate, lanthanum, strontium, barium, titanium, calcium, cuprate, which I will hereafter refer to as our compound, it was determined based on a discussion between Schlom and Antipov actually at a conference. And so, once we've done first principles analysis to make sure that we can actually create these structures, then we synthesize top candidate materials via implementation of molecular beam epitaxy, and then we verify the structures using X-ray diffraction. And then the final goal, which is the one I really came in and did the majority of the work on, was measure resistivity versus temperature to investigate the effect of these systematic changes to that lattice. So you can see M, X, and N in this formula unit. You can vary those and observe what different trends you see within resistivity as a function. So this is just one of our structures that we did end up creating to give a little bit of a preview of what we're seeing. It's a superstructure based on lanthanum and aluminate, and you can see that we made a superlattice above that of stacking different unit cells of this base unit cell formula unit. So the first real step, one that was undertaken about 2 years ago, was from Schlom and Batul Pamek out of Paradigm. And basically what they did was they attempted to make structures that fit all of the rules required by Antipov's empirical list. The way this was done was using a density functional theory calculation as well as local density approximation. That allows you to approximate what the structures are likely going to be computationally. One thing to note is that they didn't just make these structures in computation as just the pure structures, they also strained the systems. Obviously any system that we were going to make that was thin film was going to be novel in the sense that we had never seen that structure before. Most of these structures are in fact metastable, only stable in that thin film state. And so a couple of things to note. First off, all of these are different structures that were calculated. I know there's a lot of information here, so I'm going to highlight again those 3 rules I brought up before. Rule number 1 over here, that oxygen-copper-oxygen angle, that required that it was 180 plus or minus 4 degrees. And as you can see in all of these calculations, 176.55 is about the smallest or the worst angle. Everything is within that plus or minus 4 degrees. Rule number 4 over here, that you had to have the lattice parameter be less than 3.85 angstroms. Actually, most of these fail except for the C1 strained. So this is what's been strained on a 1.1% lattice parameter system, sort of like lanthanum aluminate, which would end up being the thing that we synthesize these on. And then rule number 5 over here, which is that apical oxygen distance I was talking about. Now, apical oxygen distance is kind of interesting because one other thing Antipov observed in his empirical rules was that if you were to make a plot of the best performers thus far with bismuth, thallium, and mercury-based cuprate superconductors, and then you compare our calculated apical oxygen distances against it, you find that actually we are better in calculation than any of those. So if you extrapolate on those linear trends, we're talking about maybe getting a critical temperature of around 140 to 150 Kelvin after calculation. So once these calculations were done, the next thing was, could you actually make these structures? This was done by Carolina Adamo out of Stanford University. She grew the structures in the molecular beam epitaxy room over in Duffield. And basically what was done was we repeated the structure of atomic layering 20 to 30 times. So you can imagine the unit cell, just stack it 20 to 30 times on a 100 lanthanum aluminate substrate. And that creates a film about 5 to 10 nanometers thick. Once that we've done that, we then use XRD to assess the purity of the system to make sure we actually achieved it. And spoiler, we did. All of them succeeded. And the primary structure we explored, if you go back to that table right here, was the C1 and C1 strained structure. So this C1 structure was interesting because it exhibited all the best performance. It actually exhibited better apical oxygen performance when put on lanthanum and aluminate. And so this structure right here, which I'm going to talk about a fair bit, you have cuprate layers here, you have a lead titanate sort of block up here, which is characterized by that M in the unit cell. N is the number of cuprate layers, and then X is the amount of strontium doping or hole doping. These lanthanum sites, which are these sort of teal color right here, that's where you replace with strontium to allow for more hole doping. So this is where I sort of come in full. Once we had the samples, we started with 10 millimeter by 10 millimeter lanthanum aluminate samples. So I took each of these samples, cut them down to 5 millimeter by 5 millimeter. These samples are very, very sensitive. You can imagine they're already 5 to 10 nanometers thick, thin films. Cuprates are very, very sensitive to water. So we had to run these on a really high intensity diamond saw at very low rates. It took a couple of hours per cut, but what that allowed us to do was have about 4 subsamples of each superconductor that we built. We made a total of 21 samples, and those varied in M, N, and X, so that we could compare resistivity versus temperature as a function of M, N, and X within that formula unit. Once we had the 5x5 samples, we then had to deposit electrodes. And so that was done via evaporative deposition. Since we want accurate resistivity versus temperature, we want to make sure that we get a good 4-wire measurement going. And we want to make sure it's also uniform across all 64 subsamples. And so the way we did that was we used a shadow masking technique, which is basically where you put a mask over your system that allows for a 4-wire bar sort of template to be made, almost like you're spray painting a certain design. So you have that stencil for your spray paint, and then you deposit what you want in terms of the resistivity markers and electrodes. So in our case, what we did was we put the shadow mask over that 5 millimeter by 5 millimeter substrate. We then run 10 nanometers of palladium and 100 nanometers of gold, and then we remove the shadow mask. And what that allows you to have is a perfect 4-bar measurement system where you can actually put the electrodes in. And we use noble metals as a note, palladium and gold, because we didn't want any reaction with the cuprate surface. So once all that was done, we could actually compare, what these samples look like. Here is a as-grown sample. Here is a post-dipped, post-evaporative deposition sample. You can see how small they are. You can also see a little bit of scratching. That's because this is after our actual resistivity versus temperature test, which I'll talk about in a second. So in terms of resistivity versus temperature measurements, samples were placed into a 4-wire measurement, as stated before, where we ran current on the outsides of the sample, and then we had a voltage sense on the inside. Then once we had these samples hooked up, we then proceeded to dip them in a helium dipper. That allowed us to actually deposit these samples all the way down to 4 Kelvin and take very reasonable data calculation every couple of seconds. So once we were lowering, we lowered at a rate of about 0.1 degrees Celsius per second. We were then able to take IV curves every 20 seconds. And then we did a resistance fit. Once we had the resistance fit, we treated the samples as if little bar resistors to calculate resistivity. So the setup over here is actually that helium dipper. So you can see that there's 4 wires coming out of this testing apparatus that connects to our computer setup that's running our IV curves. And then you literally slowly just drop the sample into the dipper at a rate of 0.1 degrees Celsius per second. Once we've done the dip, so we have these samples in their as-grown state, we've dipped them, we've taken their resistivity versus temperature. We then take them out of the dipper, run them to an ozone furnace, and we run those samples in 10% ozone, 90% oxygen at a pressure of 1 atmosphere, 200 degrees Celsius for 1 hour. The reason why we do this is because traditionally, if you look back at old papers of cuprates, it's clear that you sometimes need to do an oxygen anneal to make sure that you actually increase the oxygen doping within the sample. That gets everything to a proper charge balance. And so this improves the oxygen stoichiometry. And so we thought this might be a critical step. Now, before I jump into the results, I want to talk a little bit about our desired trends. First off, our stretch goal was that we would see superconducting. I mean, if we drop this into our dipper and all of a sudden you see resistivity versus temperature go down all of a sudden, then we're happy because we've actually created a sample that does exactly what we're dreaming of it doing. But this is also a first attempt at any of this type of technique. And so we realized that it was unlikely that we would find superconducting on the first run. And so our primary goal instead was to assess the impact of each of the different variables within the formula unit on resistivity versus temperature, namely M, the lead titanate layer count up here, N, the cuprate layer count, and then X, the strontium hole doping right there, as well as the impact of the anneal. So the first trend I'm going to show you is the impact of M. As a quick heads up, I'm going to be giving 3 different sets of these plots. So I'm going to quickly walk you through. On the left, you have the XRD patterns associated with the samples that we created. This is to show the crystallinity of the samples and to demonstrate that we actually got fairly high performance. On the right, you have resistivity versus temperature. So temperature starts at 0 Kelvin, goes all the way to 300 Kelvin. It's important to note that these samples match perfectly, so M equals 7, blue to blue, green to green, orange to orange. That's the case with all of the following plots as well. Also, solid lines depict pre-anneal, and then dotted lines show post-anneal. And so from this trend line, when you fix X and you fix N, what you find is that as you increase the number of lead titanate layers, you get an increase in resistivity. And I'll talk a little bit about why we think that's the case in a second. Another thing just to quickly identify is that as you anneal, it's pretty clear that resistivity drops. So that's kind of exciting. Then, if we look at the impact of n, the number of cuprate layers, if we fix m to 1 and x to 0.1 to 0.15, you find sort of a similar trend. So n equals 2 is up here, n equals 3 is up here, and n equals 4 is up here. So as you increase the number of cuprate planes, resistivity drops. Again, talk about in a second why that's the case. And then finally, as you increase strontium doping, so x equals 0%, x equals 10%, and x equals 20%, as you increase the amount of strontium in the sample, resistivity decreases once again. Now, one other result before we get into discussion I want to talk about is the impact of that anneal. Something that is sort of critical is obviously you can see resistivity tends to decrease as you increase the anneal of oxygen. But something that's also interesting that's been published in just the past couple of years is in the literature it's been shown that if you dope via oxygen, you actually might achieve a critical threshold resistivity where there's an insulator to superconductor transition. So you could imagine that you have a cuprate that's insulating, sort of like all of these curves. Like if you look at all these are all insulating, right? Because none of them are going down, none of them even look metallic. But there actually might be a transition point where if you continue to dope the sample, you can see it starts insulating, but if you continue to dope with oxygen, eventually all of a sudden it might transition into a superconducting state. And so you can basically force a cuprate into being superconducting as when it started as an insulator. And the formula we found for that calculation with help from Bollinger and Schlom discussing with Bozikin at Brookhaven National Labs is this formula right here. And so you can actually calculate a critical resistivity at which you would expect superconducting to be observed. And so going back to the plot of n, the impact of n anneal, what's interesting is we did that calculation for the n equals 4 sample, which we found was our best sample. It had the lowest resistivities. And we were able to approximate the maximum normal state resistivity to be at this line right here. Now what you'll see is when we oxygen annealed, before we oxygen annealed, you see that's pretty insulating. It's just going up the entire way. It's pretty clear on the log plot that it's an insulator still. But when we did anneal it, it actually decreased a little bit over this regime. Somewhat metallic behavior, and even at 4 Kelvin, barely insulating at all. And remember, this is just an approximation. And so we actually might be very close to superconducting behavior, even though we didn't observe it, because we're really close, within an order of magnitude, and in fact within a factor of 5, away from that value line. So in analyzing all of these results, first in considering the impact of lead titanate layer count, we found that you got similar resistivity when m is equal to 1 and m equals 4. And if you think back on the plot, m equals 7 was just the worst performer. It was sitting well in the top right corner. And we think that's probably because these lead titanate layers act as a polarizing moiety. They actually shield the cuprate layers, allowing for superconductivity to occur. But when you increase too much, what you do is you're adding more insulating layers. And you might actually hit a point where the polarization shifts away from its vertical positioning, and that doesn't allow for the same shielding effect. That one's, though, a little bit theoretical right now. Schlom and I have been going back and forth on that. So that's just a current analysis of the situation. And you find that as you increase the number of the number of cuprate layers, you find that resistivity decreases. And it seems to have the largest effect on resistivity. Going quickly back, I mean, this was our best performer, was our n equals 4 sample, and it was clearly our best performer. But we didn't vary n otherwise, and so that would suggest to us that, okay, n is really critical. This one makes a lot of sense to us as well. Even though if you go back to Antopov's rules, it says optimization was around n equals 3, we still find that, you know, if you're increasing the number of cuprate layers in your unit cell, you're getting more conducting pathways to allow electrons to flow through. And since these already are different than our bulk systems, we don't know if that same optimization as found in Antopov's rules even holds at n equals approximately 3. So n equals 4 is something that we're excited about. And then X, the addition of strontium doping, it has a prominent effect at reducing a rho, though it's important to note that, again, going back to that rule number 6 of Antopov's rules, optimization is probably around X equals 20%, and we don't think that would change between a thin film and a bulk superconductor. And so that means that, you know, we've probably optimized the whole doping. And so when you put all of this analysis together, plus you consider the importance of the anneal and how it made things all look a little bit more metallic, made it a little bit more superconducting, or maybe close to superconducting, what we can conclude is a suggestion for the next round of growths. We can't conclude any superconducting yet, but we can conclude what could be the next generation item. And so what we suggest is an m equals 4, n greater than or equal to 4, x equals 20% device, followed by a 1 ATM ozone anneal after growth. And we think that there's a chance that because of how close n equals 4 already was, and you could see that if you gave it a little bit of doping, it would decrease even further, and if you gave a perfect amount of m, so m equals 4, it'll go down even further. It's possible that we could finally pass that threshold into superconducting. And so just some quick next steps. The first next step is to test other ozone anneal regimes. We only tested ozone of 10%, 90% oxygen, 1 hour, 200 degrees Celsius, 1 atmosphere of pressure. But that actually could highly impact the performance of these structures. We don't know if we actually got optimized oxygen in there. And so I'm actually, in the next week, still going to be running tests on our n equals 4 sample, our best sample, to see if I can optimize the oxygen content. And then once we have optimization done, we're actually going to take that n equals 4 sample and send it to Brookhaven National Labs for ionic fluid gating to get a little bit more doping and also do superconductivity tests. In fact, the author of that paper with the really colorful rainbow with doping, he'll be taking a look at it personally. So that's likely going to be happening in the next week. As for some conclusions, in direct comparison to our research goals, what we found is that we were able to successfully create these structures. We were able to go about making metastable structures on a thin film base on a substrate that follow antipause design rules. Furthermore, we did not find superconductivity, but we were able to establish trends between lead titanate, cuprate layer count, strontium doping, and the impact of the anneal. And that means that we can then go ahead and do a next discovery round in a couple of weeks, months, years, what may it be. And then we were able to suggest a next round of MBE growths. So Carolina Adamo will actually be likely flying back out in the coming summer to work on growing these samples with an m equals 4, any greater than or equal to 4, x equal 20% type doping system. So we're excited about the next generation potential. Finally, I'd like to just have some acknowledgments. I'd like to thank my advisor, Darrell Schlom, who couldn't be here today. He's been an incredible help. I'd like to thank the co-authors on the paper that's currently being written, Carolina Adamo, Batul Pamuk, as well as Nye Seidner, Chen, and Moeller. Lab help, Lindsay Noskin, who helped with some of the evaporative deposition, and Kelly Thurston for sample preparation. And then thesis advisors, Professor Thompson, Professor Umbach, as well as general thanks to the Cornell Department of Material Science and to Schlom group members that helped with a little bit of the training. So with that, I think that's everything. If you would like more reference or extended manuscript discussion, please scan the QR code or go to the address l.e.me@batgur. Otherwise, I thank you for the time, and I look forward to answering your questions.
Questions?
Yeah.
So from the calculations, you expect it to be a superconductor, so what are the reasons that it is not?
So there's a variety of possible impact points. The first one is the quality of the films. Clearly we did our best, and the reason why Antipov back in 2008 couldn't do this exact same calculation is because he didn't have the modern molecular beam epitaxy techniques. But even in designing these structures, it was found that, our best quality samples still had some defects. And the thing is, in a superconductor, you really needed to have optimized control. So it's possible that's one level. Another level is that the actual lattice parameters did vary somewhat in the structures. So if there's a plot that pulled up sort of early when we were doing calculations, so right here, you have your C calculation, so like 20.689, but we found the experimental to be like 19.567. And that variability is not massive, but the fact of the matter is that, even if it's plus minus 1, that could very easily be impacting, the calculated AB, which could be impacting the copper oxygen angle. Another thing, we haven't optimized the ozone yet, and so we don't know if we have the proper doping of oxygen in the samples. So there's definitely plenty of variables that are still at play. But in general, it's still functional. We still think that we can, if we play around with enough of the variables, we might get there. So, yeah. Lewis.
So I learned recently that superconductors typically have some kind of current density limit.
Yeah.
Are you familiar or had any guesses about how this compared to current superconductors?
Yeah, so I guess given that we didn't actually identify any yet, it's unclear. All samples were tested at 1 × 10⁻⁷ amps of current run through. That was due to an optimized current density calculation that we made. It's clear that that would be an impact point, but frankly, I haven't done too much calculation. The LHC, so that runs that B, if I can find it, this guy, BSCCO lines. It would, our interpretation is it would hopefully be something like that because it's a similar Cuprate type structure. So you would anticipate that if you have the same number of layers per unit cell, you might observe the exact same general trend lines in capability.
So when you ozone annealed the N=4 sample and the temperature dependence of the resistivity got smaller. In other words, the low temperature was only a little bit higher than the high temperature.
Yeah.
But the high temperature was higher than, than the pre-annealed.
Mm-hmm. So that's something that we were pondering over quite a bit. And in fact, that's the only sample where that's the case. So in every single other sample, once you ozone annealed it, you see resistivity drop. Our current leading theory on that is that when you introduce oxygen into the sample and when you anneal it, you're doing two things. You're first probably relaxing the lattice somewhat. We don't have the rocking curve calculations. That's one thing that we've realized in the past week we wish we had, so we could do some strain analysis. But you probably relax the system a little bit. And the incorporation of oxygen also increases the C-axis of the unit cell. And so what we're currently guessing is that it's just enough change that there's no phase change, but it's basically elongating the structure, increasing resistivity just a little bit in the overall sample. But the general impact is still metallic and it's a general trend line once you've done the ozone anneal. So that's probably what makes up for it. It is a good question. That's one of our sort of...
Would it be possible that it's actually it got too much oxygen?
It is possible, yeah. So one of the analyses, as I said, in the next steps, that optimization, the first thing I'm probably going to do is increase it to 250 degrees Celsius, 300 degrees Celsius, but also might dial back the ozone and might dial back the temperature, because it is possible that maybe too much injection just caused some sort of... We didn't see any phase change. That's one thing that's been good, and it'd be pretty noticeable because the film would cloud over. But in general, yeah, that's something to be analyzed.
So these have got to be reasonably conductive films. I mean, 10⁻³ is not many semiconductors, unless they have enormous dopings, would have that kind of. I mean, are you? Maybe I want to go back to probably slide 6, where you have all the elements. Okay, I got the MBE structure.
Yeah.
So this is the, first off, this is the repeat sequence that you grew for multiple cells?
Yeah, so you can imagine that each layer right here is basically its own cell structure. So 20 to 30 times you repeat it over and over again.
So this stack of what looks like 20 different oxide films, you then repeat on top of itself 20 times.
Yeah, exactly.
To grow the film. Where is the oxygen going in when you do the ozone treatment?
So the anticipation is that primary layer point is obviously up towards the top. I guess, are you asking sort of like in general?
Yeah, what is the ozone treatment doing?
So
you're saying
currently there's two things that it's anticipated to be doing. The first thing is you can see in the general C1 structure right here that if you look at the red dots being oxygen, there's a lot of oxygen in the sample. And the fact of the matter is that some of that stoichiometry has not been achieved when you do the first MBE growth. So some of the oxygen might be incorporating into sites that were previously left flawed, in essence. But the second thing it's doing is it's filling some of the interstices, like just generally filling interstices, and it's doping the system via interstitial doping. That's something that Professor Schlom and I have talked a fair bit about, and so it's a little bit funky, and we haven't done the analysis to determine exactly what sites it's occupying or anything like that. But in general, it's just increasing the doping.
And why would that impact the electrical behavior in the cuprate layers?
So it's getting back to the published paper from Bozovic and Bollinger. The addition of oxygen, it serves as a dopant. It's adding, it's changing the formal oxidation state of the copper first off, just a little bit, as well as it's then increasing electron count and everything. And between those two different factors, that's basically what's happening here. Is you have a certain amount of doping, and then eventually you transition because you've doped it to the proper amount until you get that transition from insulating behavior to superconducting behavior.
So this is still just metallic behavior, it's not superconducting, right?
Well, I mean, it drops before, it drops to 0. So it's a normalized resistance over resistance, right? And so it is observing that general behavior.
It's going superconducting.
It's going superconducting. It's not going at like great temperatures. I mean, it's dropping at like 20 Kelvin, but it's still superconducting.
But those things are asymptotic to zero.
Yeah.
Okay. All right, other questions?
Yeah, so you're talking about optimizing the ozone to control doping to possibly get to that threshold resistivity value where you might see superconducting, but you also mentioned the second step that your Brookhaven partners will do with
Oh.
injection doping.
Fluid?
Yeah, could you
Yeah.
explain a little bit more what you expect that would do in addition to the optimized ozone that you're going to do?
So the ion fluid gating it's a slightly odd test. I'm not fully well versed in it, to be frank. But it's supposed to test basically in the regime of regular doping as well as increased doping. So basically he'll be able to verify when we send this optimized sample first our state, and then he'll be able to then test it in these sort of ion gated states. So I think the answer to your question is it's basically like he will be able to test what we see as optimized, but then he'll be able to continue to change the doping himself essentially. So it'll be able to verify a whole different range than we're currently capable of achieving.
And you'll actually, what kind of tests are you doing in the optimization state to know if you're moving in the right direction of, ozone concentration, or, you're annealing at the right temperature, too high, too low? What evaluations are you using to decide the next iteration?
So it's a somewhat janky calculation that we're going to, well not janky, janky's the wrong word, but what we're going to basically do is we're going to we know the pre-anneal state, we know the post-anneal state for that condition of anneal. So what I'm going to do is I'm going to run it again and see if it drops or increases over that line, and if it becomes more metallic. And I'm going to do it again at a different anneal, and at a different anneal, and at a different anneal. And basically I'm going to superimpose all of these lines for the n equals 4. And whichever one has the lowest resistivity or the most metallic behavior is the one I'm going to send.
And each scan, you're just varying ozone concentration or temperature of the anneal?
Yeah. So it would be, maybe we'll increase temperature from 200 to 250. Maybe we'll make the time like 1 hour or 2 hours instead of 1 hour.
Oh,
things
you
like
have
that.
3 variables then, okay.
Yeah.
That's a lot of tests.
Yeah, plenty of variables to play around with. So.
Antopov's rule, 6 rules,
Yes.
was that based off of commonalities between the highest performing superconductors to that point, or are there actual scientific reasons behind why
So,
these 6 rules?
Yeah, they are purely empirical. So quite literally, Antopov and Abakumov, they are sitting in their office and said, what can we say about every single top performing superconductor? What can we say about that mercury superconductor versus the thallium superconductor versus the barium or bismuth based,
And a bunch of others.
and a bunch of others. Yeah, and using that 17,000 different articles or whatever it was, you're able to say, okay, these all have these characteristics. So purely empirical. In fact, that's why with the comment on why Antopov left the field. 35 years studying superconductors, leaves the field, and the reason why he left the field was because solid-state chemists were like, okay, we're done with theory, we can't figure out a theory, because there's too much correlation within the materials themselves. And so, purely empirical. Which is why this was also considered the crazy Cuprate idea, because nobody wants to fund it, nobody wants to work with it, because there's no true theory guiding it. But these empirical rules are enough to be very interesting, especially when we started seeing behavior like our n equals 4 sample that was maybe getting close to superconducting.
All right, thank you.